This online lecture covers Chapter 11 on the nervous system. This is Part 3 of our nervous system lecture series, covering propagation and synapses. In our previous lecture, we talked about how action potentials are generated. Action potentials are going to be generated at the axon hillock, and then they're going to be spread along the axon or propagated along the axon. So action potentials are only going to occur on the axon of a neuron. They're not going to occur on the cell body or the dendrites. A change in membrane potential on the dendrites or the cell body is known as a graded potential. A change in membrane potential at the axon hillock and the axon is known as an action potential. In its simplest form, action potentials are going to spread because positively charged ions are attracted to negatively charged ions in the adjacent membrane. So action potentials are going to spread because positively charged ions are going to be attracted to negatively charged ions in the adjacent membrane. So if this is the site where our action potential is generated, we're going to have some initial depolarization occurring. So depolarization is that initial phase of an action potential when you have voltage-gated sodium channels opening, allowing for sodium to enter the neuron. So if we have a bunch of positively charged sodium ions here, but the adjacent membrane is more negative, those positively charged sodium ions are going to be attracted to the adjacent membrane that's negatively charged. So those sodium ions are going to spread to the adjacent regions of the membrane that are negatively charged. So this creates this wave of depolarization. This wave of depolarization, or this membrane potential, is ultimately going to decay with distance because of leakage channels. So remember that we have a bunch of leakage channels in our neuron membranes. We have sodium leakage channels and we have potassium leakage channels. So sodium is always going to be leaked into our neuron because we have more sodium outside of the neuron than inside of the neuron. Potassium is always going to be leaked out of the neuron because we have more potassium inside of our neuron than outside of our neuron. So we're always going to be leaking potassium and sodium ions. So therefore, if we have this wave of depolarization or this spreading of those sodium ions, eventually those sodium ions or that change in membrane potential is going to go back to its original resting membrane potential of -70 because ions are constantly being gained and lost. So the membrane potential decays with distance because of those leakage channels. So in other words, because we're constantly losing and gaining ions, that's going to ultimately cause that depolarization to decay and go back to resting membrane potential. So this wave of depolarization can really only go so far because eventually that change in membrane potential is going to be lost. We're going to go back to that resting membrane potential of about -70. We don't want this to happen in an action potential. We don't want that signal to decay. So to prevent this, we're going to have an action potential regenerated at every single point along that axon. So when this region here is depolarized and those positively charged ions move to the adjacent negatively charged membrane, it's going to cause that adjacent negatively charged membrane to come to threshold. And it's then going to initiate an action potential in that adjacent region of the membrane. So action potentials are going to be regenerated at every single point along that axon in order to prevent the decay of the signal. Action potentials are also unidirectional. So they are only going to move from that axon hillock to the axon. This occurs because an action potential has three phases: depolarization, repolarization, and hyperpolarization. So when this region here is depolarized, depolarization causes an influx of sodium ions. Those sodium ions are going to be attracted to the adjacent membrane that's negatively charged. It's then going to bring that adjacent membrane to threshold, causing an action potential at the next point along the axon. That previous region has now gone from the depolarization phase of an action potential to the repolarization phase of an action potential. So during repolarization, we're going to be losing a ton of potassium ions, bringing that membrane potential back down towards -70, or the resting membrane potential. So action potentials are unidirectional and are only going to move from the axon hillock towards the axon terminal because repolarization is going to prevent the spreading of that action potential in the opposite direction.